As promised, let's push into rotational kinetic energy. Essentially, rotational kinetic energy is pretty much the same as kinetic energy, and we've seen this with all of our rotational cases, where they've all had a linear analog. Really, when we're talking about rotational kinetic energy, we're really saying it's half mv squared for the linear case, but we're really substituting for v. So we're saying that we're looking at essentially mr squared omega squared. Now, mr squared, however, becomes half mr squared in the case of the rotational energy, but the kinetic energy term of mr squared actually winds up becoming the value for the inertia, the actual expression for inertia. So not only can we say Ke is half mv squared, where v is equal to omega r, and then end up with 1 half mr squared omega squared, we can also say that with the moment of inertia I, we can say Ke is 1 half I omega squared. Sorry about the font, that's an I. Before we proceed, we talked about centripetal force in the previous section. Quite often, people refer to this as centrifugal force. This is actually a different effect and is actually the result of a body's inertia. So when you whirl a body in an arc, it wants to move in a straight line, but it actually is held and constrained to go in that arc, and that's what gives you a centrifugal force. It's actually a byproduct of Newton's first law. So if you take a bucket of water and swing it in a huge arc, it can at one point become vertical and upside down, and the water will not come out. So this is centrifugal force. It's not really a force, but it's to do with the inertia of the object. This is not anything to do with centripetal force that we discussed previously. So, in terms of inertia, what is this? Well, it's the measure of a body's resistance to changes in its velocity, essentially the opposite of our momenta that we were talking about. So the mass of the body is determined by how it the momentum and inertia of a body is really related to how it responds to velocity, how it responds to forces. So larger mass, less acceleration. In momentum, the mass represents the difficulty to maintain your velocity in the mv equation. Inertia really is the resistance to a change in velocity, the resistance to a force being applied. And this is complicated depending on the shape of the object. So take something like a thin uniform rod of material. And we sort of discussed that kind of thing when we looked at center of mass. But here's our thin rod, and here it is sitting in the XYZ plane. And it's going to have a rotational axis. It's going to spin around in this case. And if it spins around, we can define all the things we have previously in terms of our rotational system. So here's v, our tangential velocity, and that's going to be equal to omega r. And of course, omega is the speed at which it's rotating in radians per second. We've got a length, and we've got some mass element. And as you would expect, based on our discussion on center of mass, we will end up summing along those mass elements and looking at the distribution of mass and relating that to the inertia. Here, I equals 1/3 ml squared, where L is the length of the rod. So, essentially, it's 1/3 ml squared here. Now, that's when it's rotating about one end. So if we tether the end of this rod and we rotate it, this is the value we'll get for inertia. If you do it the other way, and you actually put this here, and rotate about the center, you'll end up with a different value. And what you'll actually end up with is a value of 1/12 ml squared. This is essentially like its 2-point masses attached by a rod. So, depending on how a body rotates, which axis it rotates around, depends on the moment of inertia. Your moment of inertia is dependent on that particular fact. And that makes things a little bit complicated and very system specific. So say something like the inertia of a hoop. This is different to the inertia of something like a solid disk. So it behaves as if all mass is equal at r, which is true. We're looking at a hoop, so all mass is equal at radius r, and it's all concentrated right here. If you look at the inertia of this body, and you sum up all the little mass elements, and remember this is just a hoop, it does not behave like a flat disk, then I will be mr squared, which is one of the simpler definitions. Now, if we apply Newton's laws, we can even express this in terms of the torque. And the torque is something we're coming to. Torque is the twisting force about the point that the system is actually revolving, about the rotating point. So torque would be the twisting force about this central point. And it's a force, a circular force. And it's equal to the inertia times the angular acceleration. Torque is equal to I alpha. We're going to see a new definition of torque later on, so bear this in mind. So our rotational inertia gives us the lever arm moment, some distance multiplied by a force. And that means we can say, well, does mass resist rotation the same way it resists acceleration? And the answer is kind of, yeah. So if we look at our F equals ma, we can say that the linear acceleration, essentially being replaced by alpha, becomes torque over mr squared instead of a equals F over m. So torque changes motion. Inertia resists motion. And that means you can look at rotational kinetic energies and look at the inertia of any body based on its mass distribution. Now, given our time limitations, we're going to actually truncate some of this material. We would usually spend a fair amount of time integrating over various bodies. So as you can see here, the inertia for this long rod, which is rotating about the z-axis here, would be r squared dm. Now, what this really means in terms of our material is every shape, every distribution of mass will have a slightly different expression for the moment of inertia in a rotational sense. So take our hoop. We saw this previously. I is equal to mr squared. Take a thick hoop now, an annular cylinder, and you're talking about 1/2 m times the difference in the radius squared. A solid cylinder behaves differently to a hoop at 1/2 ml squared now. Again, solid cylinder now, if we rotate it about this axis instead of this axis, has quite a different expression and quite a bit more complicated, taking into account both R and L. Thin rod, again. Solid sphere, I 2/5 mr squared. Thin circle shells, hoops about the central axis now instead of about the axis as if it's rolling. In this particular case, I is equal to mr squared for both of these. And then you can look at flat slabs and how those rotate. So given the complexity involved here, like I said, we are going to look at the effects here more rather than just going through every single geometry, given that we are under some time limitation. So essentially what you're doing for the moment of inertia is the sum of mr squared for all the particles in a mass, in a solid. And any solid object contains mass distributed at different distances from the center of its rotation. So that's a lot of words. I've said a lot of things. What does this mean for us? So take a rolling disk here. What does this mean about how energy is used in an object that is moving? So here we have a 1.2 kilogram disk with a radius of 0.1 meters. It's rolling without slipping, and its linear speed is 1.41 meters per second. We want to find three things: the translational kinetic energy, the rotational kinetic energy, and finally, the total kinetic energy of the disk, spelled with a C in British fashion. So what we're saying is if we look at the moment of inertia of a body, it kind of acts as an efficiency factor. And if we look at the kinetic energy of this object, some kinetic energy will be used in terms of translating the body, some kinetic energy will be used in terms of rotating the body. So the distribution of mass will kind of tell us how much energy goes into making this thing spin about its axis, and how much energy goes into actually making the object move. So let's take a look. So we've got our 1.2 kilogram disc, and it's 0.1 meters across. Well, its radius is 0.1 meters. Its velocity is 1.41 meters per second. The translational kinetic energy, this is the energy with which it's moving from the left to the right, will just be half mv squared. So that's half the mass times the velocity squared, and will give us 1.19 joules. Now the rotational kinetic energy here is going to be half I omega squared. If we substitute in for I, this is half mr squared multiplied by v over r squared here, and that's going to give us 1/2 times a half mv squared. If we go through this, we can then say 1I omega squared is equal to 1/2 1.19 joules, which will give us 0.595 joules. That's the rotational kinetic energy. So, in terms of the total energy budget here, we saw 1.19 joules of kinetic energy going into moving this object, and 0.595 joules of kinetic energy going into rotating this object. That means the total energy budget of this system is just a sum of the two. If we sum the two, the total kinetic energy is 1.19 plus 0.595, which will give us 1.79 joules. So, as I said, when an object moves, some of its energy will be used in rotation, some of it will be used in translation. So take this particular situation. If we take a solid disc and a hoop and take them to the top of an incline. Now, you can go back and you can look at all the forces on an incline, and we'll find out there's a sine theta, an mg sine theta component acting down the slope. Now remember, when we talked about gravity, we said that gravity was invariant of mass. Now, the mass of these two objects is exactly the same. So, by our normal Newtonian thinking, we should say mg sine theta down the slope will be the same for both of these objects, and that is true, it will. The kinetic energy that's imparted to this will be the gravitational potential energy converted to kinetic as this object comes down the slope. So the energy given to both of these two by gravity will be the same. With that in mind, which one of these objects will reach the bottom of the ramp first? The disc or the hoop? So stop, think about it for a second. Which one? If you answered both, because I just previously sort of alluded to it, then you're wrong. They will not reach the bottom of the ramp at the same time. What will actually happen is the disc will reach the bottom of the ramp first, the hoop second. But how does this happen, Dr. Horn, you incredibly talented polymath, you may be asking? Well, both are given the same amount of energy in terms of mass times gravity times height, mgh, gravitational potential energy. And that is converted into kinetic energy to both of these. Now the disk uses more kinetic energy in terms of its translation. Because of the moment of inertia of the hoop uses more kinetic energy in its rotation, which means there's less kinetic energy left over to translate it down the slope. So, the energy that's lost in rotating the hoop slows it down and gives it less energy for translation and gives it a slower velocity because its mass stays constant. So just as a proof, if we take a look at the disc and the hoop, same mass, starting from rest, roll down an incline. The incline's height is 0.82 meters. We want to find the velocity of each object at the foot of the ramp. There we are. There's our situation. Crude diagram up here of the situation we just looked at. Find the velocity of each at the foot of the ramp. So, first question. What's the potential energy at the top of the ramp? Their masses are the same. So m times g times h. mgh is now a kinetic energy term plus an inertial term. So kinetic energy will equal half mv squared plus 1/2 I omega squared. We're going to substitute in here and do things in terms of v. So let's sub in for a v over r here in omega, and we'll end up with mgh is half mv squared plus 1/2 I v over r squared. That means for the disk, I is equal to half mr squared. So mgh is half mv squared plus half mr squared, which is our I term, times v over r squared. Now we've got mass all over the place here, so let's get rid of it. Simplify things a bit. That'll give us gh is half v squared plus 1/4 v squared. That'll give us a total value of 3/4 v squared is equal to gh. We wanted v. Let's not forget what we were trying to do. So v is 4/3 gh. That's equal to 4/3, 9.8, times the height that this was dropped from, which is 0.82 meters. That'll give us 3.3 meters per second. For the hoop, we can use I equals mr squared here. mgh will be half mv squared plus half mr squared v over r squared, as we saw for the disk. And so then mgh, cancel our m's again. gh will be half v squared plus half v squared, which will equal v squared. So v is equal to root g times h. Let's substitute in. This is 9.8 times 0.82. That gives us 2.8 meters per second. So if we follow the calculations through, the disk will end up traveling faster at 3.3 meters per second than the 2.8 meters per second of the hoop, even though they are the same mass. And like I said, we are truncating some things. So if you look at the inertia of a body, especially the rotational inertia of the body, how mass is distributed really tells you how it's going to behave in terms of its rotational dynamics, in terms of its kinetic energy. Take something like the Earth. It's not a uniform body. It's liquid in the center, and then there's solid bits, and then you've got gas on the outside. But it rotates, and its angular momentum that we'll come to soon is conserved, and it rotates fairly uniformly. More complicated are things like asteroids that we just saw, peanut-shaped weird objects, and in those cases where we're looking at something like that rotating around, you have to look at two centers of mass, and you have to say, well, I is equal to ICM, what's the inertia of the center of mass, plus some correction for the mass times h here, the distance between these two axes squared. So in the case of something like a very non-uniform body, it's much easier to integrate across it. That means looking at these complicated systems can be very difficult if you are, say, wanting to go into orbit or look at the dynamics of a body like this. We're not necessarily going to get into that, like I said, because of our time constraints. What we are going to do is define our next value, which is that of angular momentum. Now, angular momentum that I mentioned briefly in passing is given as L, and this is m times v cross r. And this is that cross product we saw previously that I said was going to return and be used here. So essentially, L is mvr sine of theta, the angle between V and R. So when we're looking at angular momentum, this is again our rotational analog to momentum, linear momentum P equals mv. Now, if we look at this equation, mrv is our magnitude of L. It's a mass, it's a radius, it's a velocity. Now, if you think back to conservation of momentum, we said that Pi was always equal to Pf. And that is true of angular momentum. Li is equal to Lf. That means if angular momentum is conserved, here you've got a guy in an office chair, and don't tell me you haven't tried this. If you are spinning around in an office chair and you pull your legs in, you will find you will go faster. If you put your legs out, you will find you will go slower. The reason being that angular momentum is mvr. That means if you increase your radius and angular momentum has to stay the same value, then v will go down. If you decrease your radius and pull your legs in, then v must go up. And it's this kind of thing that keeps planets rotating for eons, for billions of years. Their mass doesn't change very much. The mass of a planet is very big. Even adding asteroids to it doesn't appreciably increase its mass. So if we keep m constant and r relatively constant, then it will carry on rotating at the same velocity that it always does, unless of course something catastrophic occurs. And just as a reminder, remember our cross product was A cross B, meaning that as a maximum, if we have A 90 degrees to B as two vectors, then the third vector, A cross B, will end up being 90 degrees to those two. So think about this in terms of, say, spinning a coin. If you spin a coin on a desktop, what you're doing is applying a velocity at 90 degrees to that coin, to its edge. It's a tangential velocity. That means you're applying it 90 degrees to it. So that you'll end up with angular momentum vector being straight out the top of the coin. You've got the radius, you apply your velocity at 90 degrees, then L is out of the top, and you'll end up with your coin spinning around an axis. So of course, with angular momentum, A cross B is AB sine theta. So L is equal to mvr sine theta. And that sine theta would be the angle between V and R. Angular momentum is quite often also defined in terms of the inertia of the body. We've seen this a couple of times in terms of inertia. I think given the time frame we're looking at, we'll mostly stick to looking at L being mvr, but you can also exploit the inertia should you need to, where L is I times omega. That means there's multiple definitions of angular momentum. L can be mvr or mv cross r. This can be mr times omega r, or mr squared, or I omega. So, as I said with angular momentum, there's a couple of examples here. Take this skater. If she is rotating with her arms out, we have m cross v cross r. The extended arms mean big radius and lower velocity. If L is conserved, in the second case, her arms are brought in. That means her radius has decreased and her rotational velocity has increased. So like I said, typical example is an office chair. Pull your legs in, you rotate faster. Put your legs out, you slow down. Try it yourself. I am not responsible for any injuries incurred from playing in office chairs as a result of this class. So, we want to finish up soon in terms of talking about rotational systems and working our way into dealing with rotational forces and torque. So, We have talked about levers before and looked at different lever types and looked at pulleys and mechanical advantages. And that mechanical advantage was given as a ratio of two distances. The distance from a force to the rotation or fulcrum point of a lever and the distance from the gravitational force or the load that was applied and the load that was put in. So we end up with two values. So a simple mechanical advantage of this particular lever system, we've got 15, we've got 5. What we'll end up with here would be 15 over 5. The mechanical advantage here would essentially be 3 or 1/3. So you can essentially balance something like a lever, but dealing with the forces in terms of a linear case is quite complicated. So finding the center of mass of an object and then applying a force to it and looking at its lever arms is relatively important. And I like, as I said when we talked about levers, instead of messing with force times distance as we did in that first case, what we'll really do is talk about things in terms of torque, Torque, and the rotational force on an object. So take these two objects. What we've got here is a mini, very low to the ground, and a lifted truck here. Now, this truck here, as anybody who's driven this kind of thing will know, is much more likely to tip over if you throw it into a curve than this low to the ground little mini. Why is that? Well, if you throw it into a curve, what you'll end up with is a lever arm moment set up from here at the edge of the tire to the center of mass of the object. That means if a force is applied to the side of these two objects, the lever arm moment, which essentially will be this force multiplied by this distance, will be much stronger for this object than for this one, causing this vehicle to flip and this vehicle to probably translate to the side. That's why sports cars are low to the ground and trucks tend to be higher. So if we were looking at the twisting force, which is the force about this point on the vehicle, we would have to look at F times R to the center of mass of both objects. The other thing that will affect the dynamics of such a vehicle would be something like rotational inertia, and that is the object's resistance to rotational motion in the same way as when we just talked about. Now when we're dealing with levers, there's three classes of lever. These make for excellent bonus questions, thermonuclear hint there, and they're based on the position of the fulcrum point and the position of the load. And like I said, we're going to talk these through and then eventually reduce it down to looking at this twisting force. But a class 1 lever has a force applied here, a fulcrum in the center, and a load on this side. When this distance and this distance and this mass and this force are equal, then you'll end up with balance being attained. A class 2 lever, here we've got a force, a load, and a fulcrum. An example of this kind of object might be something like a door. If you apply your force right at the end of the door, the load is primarily in the center, and this will make life much easier to open and close that door. If you push a door very, very close to the hinges, you have to apply a lot more force. That really is saying that force times distance gives you more torque. But here's our class 2 lever, and the primary difference between the classes is the position of the force that's applied, the position of the fulcrum, the twisting point, and the position of the load. So class 1, force, fulcrum, load. Class 2, force, load, fulcrum. And for a class 3 lever, load, force, and then fulcrum. What I want you to do is take a look at various examples of these different levers and have a quick idea of which type and certain objects would be and how to identify class 1, 2 and 3 levers. Like I said, nice bonuses come out of this that aren't particularly complicated. But if you're looking at objects like this. Here's a class 1 lever. Here's a crowbar, force, load, fulcrum in the center. Class 2, here's our fulcrum, here's our load, here's our force. And a class 3, your load, force, and fulcrum. There are some dynamic objects. Take something like a human arm. You can actually move your arm in a couple of ways. You can either put it outright so the shoulder becomes a pivot point. You can look at the elbow as a pivot point. So things like bodies which are adaptable can have multiple different types of, well, I say multiple, can only have one of 3 different types of lever arm moments. And looking at the attachment points of such things is a major body of work. You could look at the joints, you can look at this, and this is of course a major field of study looking at rotational kinematics of joints and replacement joints. Like I said, when we were discussing rotational motions, I wanted to sort of stick with that theme. And when we looked at levers, I kept saying, I want to come back and discuss these in terms of rotational motion. And this is what we're doing. So if we take this system, here's our lever, R, and here's our load, providing a force on this arm. Now we've already defined this, but in linear terms. What I like to do is do things in terms of torque. This is the twisting force about the fulcrum point, instead of worrying about all those distances and forces. And the magnitude of your torque is R, this distance, times the force. And like I was saying, if you go and push a door, it's a lot easier to push if you push it over by the handle than it is if you push it over by the hinges. The reason being that the torque here will be multiplied by R. The torque is a force multiplied by a distance. So the torque, the twisting force about this point, is much, much higher when you apply your force over here than over here. So here, the force in the linear terms will be the same, but the torque, the twisting force at this particular pivot point, will be a lot smaller because R is significantly reduced. So torque is an angular force, and that causes a change in rotational motion. Really, torque is R crossed with F. It is that cross product again, which really becomes RF sine theta. And that really depends on the angle at which the force is applied. If it's applied 90 degrees to R, then sine theta is a maximum and 1, and torque just becomes R times F. So what's the real story behind this? Well, anyone who's taken their car in and given to somebody who's used an impact wrench to put your wheel on, and then you've had to change the wheel, has probably experienced this very problem. So, when someone uses a mechanical wrench and puts these nuts on very, very tightly, you can't get them off. Now, you can take this wrench and you can apply as much force as you want to this. You can get your biggest, heaviest friends to jump on this, and you can't get these nuts off. The maximum amount of force you can apply from to here is not sufficient to remove the nuts, to apply a torque which can take them off. Now, this radius here is limited. So instead of having a lot of heavy people jumping on the end of this small radius, a way of increasing the torque, the twisting force about this nut, is to leave your force the same and increase R. So that's what this guy has done here. And he's incredibly happy about this discovery. I have no idea who he is. I just borrowed him for the purpose of this talk. Now, he's taking this wheel off. He couldn't apply any more force to the end of this tiny little wrench, so he got a very long piece of pipe. That means the torque that he's applying to these nuts has now increased enormously because this R has increased. So if we're looking at something like a wrench, Here we have our wrench. Here we have our nut that we're applying the wrench to. We're applying a force then at some angle. So if we apply a force, we would have essentially two components, an x component and a y component. We don't really care about this x component. What we care about in terms of the twisting force here is what forces are being applied downwards or upwards in order to turn this particular nut around, in order to provide a torque on this object. And that torque here will be whatever force we have here times r. Hence, torque is r f sine theta. Geometrically, you can play with the line of action here, and you can sort out a whole load of much more complex physics. We're going to really stick to using torque being Rf or Rf sine theta for our case. Something that should be noted is that torque can be applied in a clockwise or counterclockwise direction. The reason I mention this is that when we look at modern engineering, most cases, not all, but in most cases we manufacture a thread where we turn it left and we loosen a nut. If we turn it right, we tighten it up. Now that is an engineering choice. Torque can be applied in any particular direction. There's nothing in nature to say you can't twist something left as much as you twist it to the right. So here we have a situation where a mechanic is pushing 90 degrees on the end of a 0.15 meter wrench. If the mechanic applies a force of 230 newtons in a counterclockwise rotation, I realize the diagram is backwards, what is the torque applied to the bolt? Well, our torque is going to be F times the distance of 0.15 meters sine theta. That means torque will be 230 newtons times 0.15 sine of 90 in this case. So torque becomes 34.5 Newton meters. So the unit of torque is a distance times a force, Newton meters. So torque, as we said, is directionally independent. It doesn't matter if you apply it left, right, or counterclockwise and clockwise in terms of the twisting force. You can relate torque to acceleration. Remember, F equals ma still applies. Torque is a force. So torque is F times r. If we apply ma, then torque can be ma times r. That means if we can write it in terms of F equals ma, we can write it in terms of an acceleration. The acceleration in this case will be a tangential acceleration, which will be r times alpha. So torque can also be mr alpha times r, which will give you mr squared alpha. This is used a little more rarely, and usually torque is equal to r times f. It's usually quite sufficient. Or you can figure out what a is here and substitute in. But this is a version that you might see, or could derive should you need it. You can also see it in terms of inertia. If we can put it in terms of alpha, we can put it in terms of inertia. So torque can also be equal to mr squared alpha, where I is mr squared, so torque is equal to I alpha. As I said, we're simplifying things of late, given the current situation. So I would say concentrate mostly on looking at torque being F times R. But these are variants you may see somewhere else. So let's take a look at another torque calculation. And I want people to visualize this in the right sense. Here we've got two wheels, and they're stuck together. We've got a radius R1 and a radius R2. R1 is from the center to the edge of the orange disc, and then this other disc is glued to the front of it and is from the center to radius R2. The forces then, we've got one force applied to the orange disc pulled this way and another force applied to the gray disc pulled this way. That means this F2 is going to want to rotate the disk this way, and this F1 is going to want to rotate the disk this way. The question is, what's the total torque on the system at the origin, right at the center? And remember, torque is equal to R times F. So you do have to think about the directions of F. And the error that most people make here is to simply calculate two torques and add them up. Now, that's not incorrect, but what you have to remember is the torques will be in opposite directions. F2 will have a rotation this way, F1 will cause a rotation this way. So to simply have two torques added would be incorrect. The total torque at the origin will be torque 1 minus torque 2. The torque generated by F2 at R2 will be opposite to the torque generated at F1 at R1. So let's put some numbers to it. If F1 is 5 newtons and R1 is a meter, F2 is 6 newtons and R2 is 0.5 meters. What's the total torque around the origin? Well, the torque, as we just specified in the previous slide, is tau 1 minus tau 2, torque 1 minus torque 2. So what's the torque around the origin? Well, it's going to be 5 times 1, which is going to be 5 Newton meters. Torque 2 is going to be 6 times 0.5, which will give you 3 Newton meters. So the total torque will be 5 minus 3, which is 2 Newton meters. That means this is positive, and our system is going to rotate in a clockwise direction. So remember, this will end up with a 5 Newton meter torque this way and a 3 Newton meter torque this way, giving you a total of 2 Newton meters and rotating the system clockwise. So like we said, the torque is directionally independent, and you can calculate it by finding the total in either of the torques in all directions. And that's how I like to really solve rotational systems in this sense. We can, of course, relate our torque to work and to kinetic energy. So as we spin an object, we'll do work on it. The kinetic energy will increase. So from work equals force times distance, we can say S is R times theta, so work is FR theta. You could also put that in differential terms and say dW is torque times d theta. Of course, if we can define work, we can also define power. And power will then become dW by dt times torque times d theta by dt. We'll probably not really employ this given the time allowing. So let's take a look at one last example of torque. So we could solve this essentially in terms of a linear system, but why would we when we can use torque to make our lives easier? So if we have an object sitting on a shelf, or a piece of scaffolding in this particular case, and that scaffolding is actually tethered to the wall with a cable like this. That means this whole system is static and everything is standing still. We could look at the sine of this angle, and we'll have a 90-degree angle here and determine this angle and figure out the forces here. What we could also do is say, well, what's the torque about this reaction point on the wall? So what we've got here is an object, a mass m, sitting so many meters, x meters away from the wall. The shelf also has a mass of capital M, and it's got a width of L, so its distance here is L. What's the tension in the wire supporting the shelf at angle theta from the vertical? And like I said, you could solve this in a linear case and find out angles and sort this out. Or you could just use the torque around this point on the wall. So the situation is, we'll have gravity acting on this system. We will have mg, big mg, which is the force acting on the shelf. Little mg being the force due to gravity acting on the object. We've got a distance x, so we can look at the force with relative to this reaction point, and that will give us a tension in this line at some angle theta. So to do something like this, first we say we have the weight of the beam, mg, and then we have the weight of the object, little mg. We've got L, which is the length of the beam, and then we've got the angle of the support cable with the wall. So if we resolve the forces at the reaction point R, we can say here R is TL cos of theta. If we resolve the downwards forces here, this will be mg times L. So this is a torque due to the actual shelf. I keep saying shelf. The actual scaffold is actual beam here, and then you'll have mgx to this distance. What we'll then do is say, well, let's set the torque at R equal to the downwards force. So we're then balancing up the forces. The TL cos theta, which is the tension in this line, with the torques downwards. So this line is pulling this upwards like a drawbridge and giving you a torque this way, and this shelf plus this mass is giving you a torque rotating the system this way. If you cut this string, this thing would swing down and slam. If you increase this tension, this would swing up and slam. So these two equal one another, and instead of doing this linearly, we've said that R here, the reaction force at this point, will be TL cos theta, and that's going to be equal to mgl for the shelf plus mgx for the object. Think about the problems we've looked at. There's a lot of them in here. Take a look at them in PDF form and read through this section in the book. It's not particularly complicated. You just have to make sure your definitions are correct. Make sure you're in radians. Don't overthink the definitions too much. There's a lot of definitions, but they actually simplify down well if you look at the system. And the biggest flaw when people start doing rotational motion is trying to apply linear motion when you should be solving a rotational problem.